Good morning, everyone from Philippines here, and welcome to this webinar. Um, just to remind you that you are in a listen-only mode to avoid unnecessary background noise. But if you have questions, you can type in anytime in the chat box your questions, and we will be answering it after this presentation. So today, our topic is about the basic of CT, VT, and CVT testing, and it will be presented by Michael Evangelista. Oh, sorry, it's me. And we have panelists. My colleague from Indonesia, Sumedi, will help me answering your questions after this presentation. So let's start. So again, this is Michael Evangelista, and I'm one of the APAC applications engineer. And our topic for today is the basic of CT, VT, and CVT testing. Now, going to the agenda of this presentation, we will be talking about the current transformer on how to test it, the basic and fundamentals of it. We will be also discussing about the voltage transformer and the capacity voltage transformer. And as you can see here, there is a bracket here, and these transformers, we are referring it to instrument transformers. So the agenda will be testing of these transformers here. Now, first, let's define what are instrument transformers. So like I've said, if you have the CT, VT, and ZVT, these are the instrument transformers. And according to Wikipedia, I got this definition from Wikipedia. Um, these are high accuracy class electrical devices used to isolate or transform voltage or current levels. So the most common usage of instrument transformer is to operate instruments or metering from high voltage or high current circuits and safely isolating secondary control circuitry from the high voltage or high current. And the primary winding of the transformer is connected to the high voltage or high current circuit, and the meter or relay is connected to the secondary circuit. This is from Wikipedia. So in short, CTs, VTs, and CVTs are the sensors of the system because it gives the information to the relay, to the meter. So they serve as the sensor of the system. It detects usually the current, the voltage, and the frequency, and it feeds the information to the relay or meter to save level of magnitude. Now, the most complex or complicated among these three instrument transformers are the CTs. So I'll give more focus on this type of instrument transformer. So a CT is defined as an instrument transformer with its primary winding connected in series with a conductor carrying the current we want to measure and control. And CT are used to supply a reduced value of current, and it is typically 5 amp or 1 amp at full load, to meters, to protective relays, and other instrumentations like transducers. Of course, it must be in a low-level signal to protect our personnel and apparatus from the high voltage and allowing us a reasonable amount of current in each of these applications. The secondary of the transformer will supply a current that accurately reflects a proportional value of the primary current with the smallest phase shift possible. Normally, in some cities, we have two different cores. We have the metering cores and we have the protection core. In this example, as you can see in this diagram here, this CT is just one CT, but it has two different cores. And for the protection core, it is connected to the where the relay is being connected. And for the metering core, that is where the metering or the meter is connected. So again, we have two types of CTs, the metering and protection. Now let's talk about the metering CTs. These CTs is used for revenue, for money. So with that, it must be high accurate. So these CTs is normally with a range of 10% to 100% accuracy of the full load CT rating. So again, this is used for the billing of energy and normally used by electrical utilities. Now, the other class is the protection class CT. So the protection class CT, as you can see here in the diagram, like I've said, instrument transformer are the sensors. So from the power system, the voltage or the current transformer detects or serves as the sensor, and this instrument transformer will give signal to the relay, and so the relay will decide whether the system qualities are normal or abnormal before it gives tripping signal to the circuit breaker to open. So the IEEE C57.13.1 Series 2016 specifies that protection CTs need to maintain plus or minus 10% ratio accuracy over a range from 1 to 20 times the rated secondary current at the specified burden. So when we talk of 1 to 20 times of the rated current, that must be a fault current. So meaning for protection class CTs, what we need is a high burden CT. Okay. Oops. Now, what is the difference between the current transformer versus voltage transformer? So when we talk about the voltage transformer, this is a similar or very the same as the power transformer, where you have the primary winding, you have the winding there, and the secondary winding. While when we talk of the current transformer, then we have the primary conductor here, which will be served as our primary winding actually, and we have a core, normally a circular core, and it is being wrapped by a magnetic wire, and that composed of our winding. Some construction of the CTs, as you can see here, we have the window type, the bar type, split core, and the Rogowski coil. Now, talking about the CT ratings. So as you can see in the nameplate, now let me talk first about the ANSI rating. So you have these three number and letters, as you can see. On the first position, this determines the accuracy in percent. The second position, which indicates a letter, this is an indication of the class of the CT. So in this example here, we have B, and that means that class B is a metering class. And the third number, as you can see here, is the maximum burden in ohms. Right? So that is just for the metering class. Now, why I need to mention this one? Because when we do testing of CTs, these are the numbers that we need to verify. These are the numbers that we need to check. That's why we do the testing. Now, talking about the protection class here, it's the same. The first number determines the accuracy in percent, and then the letter on the second position, that is the class of the CT. So if it is C, then that means that is a donut type CT with calculated percent accuracy. If it is T, that means it is a tested. So T stands for the tested in factory. H, that is accuracy applies to 20 times the CT nominal amps. And L, accuracy can vary up to 4 times the rating depending on the load. So in this example here, again, on the third position, this is the number that determines our burden. But for protection class, this is the maximum burden in volts at 20 times the CT ampere rating, which is 100. So that means when you see the 100 number here, the number 100 here, then that means the maximum burden is 1 ohm, because this one for protection class determines the maximum burden in volts at 20 times the CT amp rating of the CT. Now, it's different when we talk of the IEC CTs. With the IEC CTs and the nameplate, you will see this label, something like this. So the first number, as you can see here, 15 BA, this is the burden, and this is the continuous BA that the CT can handle. And it's very clear on the second part, we have the class 10, then that means that is the accuracy class of the CT. And this P here is the protection class, or indication of that it is a protection class. And this 20 here is the accuracy limiting factor. Now, comparing the two, and we have this table here that corresponds or equivalent of the ANSI to IEC. So, in example, if we have a C800 CT, that is equivalent to IEC CT, which is 200 VA and 10 P10. When we talk of C100 or plus 100 volts CT, that corresponds to 25 VA, 10 P20 IEC CT. Now, let's go on to the testing of the CTs. What are the tests that are being conducted for CTs? Number one, what we have is the insulation resistance. Again, number two, we have the winding resistance. It is very, very important test. We have the saturation excitation test, also very important, and everything is very important here for the field test. We have the ratio and phase deviation. We have the polarity. We have the burden test, and we have the CT demagnetization. Well, actually, the CT demagnetization is not a test, but a good tool or a procedure to do in order for us to get a better and reliable test result. In some other cases, or some other customers used to test the insulation power factor of the CT, right? Now, let's talk about the test that being defined by the IEEE standard C57.13.1. So this standard is a guide for field testing of relaying current transformer. These are the important tests as defined by the IEEE standard. First is the ratio test. This test is intended to prove that the ratio is correct as installed, as specified, and if it is a multi-tap, it's correct and available. Next test is the polarity test. This test proves that the predicted direction of the current or secondary current flow is correct for a given direction of primary current flow. This is essential where currents are summed, compared in differential mode, either electrically or magnetically, or where currents and voltages are compared within the relay or electronic device. It is defined by ANSI standard, the insulation resistance test. So we all know that this is a very important test to assess our insulation. So with the CT insulation resistance test, we consider the primary winding to secondary winding insulation. We do the testing for primary winding to ground insulation and the secondary winding to ground insulation. Another important test is the resistance measurement. This test confirms that the DC resistance of the CT secondary winding is within specification and that there is no high resistance connection in the CT or the wiring connected to it. Sometimes this resistance measurement is being used to calculate the burden in consideration of bus differential relay setting. So we need to check the resistance of the CT so that we can have or we can compute the correct safety factor when we do the setting of a bus differential relay. Another test is the burden test. The burden test can be done only with current flowing in the CT secondary circuit, preferably near the rated current. And this test confirms that the CT is capable of supplying a known current, dictated by the turns ratio into a known burden and maintain a stated accuracy. Another important test is the excitation test. This test confirms that the CT as supplied is of the correct accuracy rating and has no shorted turns in the CT, and no wiring or physical short circuits have developed in the primary or secondary windings of the CT after installation. Normally, the manufacturers provide these curves and should be available so that the actual result can be compared with those curves when we do the testing for the excitation test. But before we do the testing of the CT, of course, it's very important we need to consider the safety first. We need to protect our personnel and equipment, and we need to follow the local safety policy and equipment operation instruction. And very, very important is to check the grounding, the locking out, and if the CT is already installed in the system, that we need to sure that our tagging is correct, right, for safety purposes. Now, how do we do the insulation resistance test? This method is based on the IEEE C57.13.1-2016. So as I mentioned a while ago, we do the primary to ground insulation, we do the secondary to ground insulation, and we do the primary winding to secondary windings test. So if you do the insulation resistance test, we measure the resistance value should be compared with those of similar devices. So if you have different or several CTs in the stockyard, then what we can do is to compare the result of insulation resistance of each CTs available. And another thing, if we have a lower reading, then we need to carefully investigate what happened. So the generally accepted minimum insulation resistance is 1 mega ohm. And one of the most common reasons why we do this insulation resistance is to check the presence of the moisture in the CT, or if there are contaminants in our CTs. And the recommendation of the ANSI standard, if it fails or if we have a low resistance reading, then that equipment should be dried out and retested. Okay. Winding resistance test. This measures the CT winding resistance from one external terminal to another terminal. So as you can see in the CT, we have the primary winding or the primary conductor, primary terminal, and we have the secondary terminals. So when we do the resistance winding, we do from external terminal on the secondary going to the another terminal of the secondary winding. And with that, we inject a test current into the winding, and the corresponding voltage drop is measured, and we just use the Ohm's law to calculate the resistance. So a DC test will always cause a residual magnetism because it is a DC current that we injected. So it will magnetize our CT. So as per recommendation of ANSI standard, we need to demagnetize the CT after such test or after the winding resistance test. So when we do the demagnetization, we use it to eliminate the effect of the residual magnetism. In our case, or in our equipment, we use a variable AC source to ramp the secondary RMS voltage up to the CT saturation, as you can see in the diagram here, then slowly bring back the voltage to zero. So ideally, we need to bring back from saturation to the zero voltage, and in that point, we have this flux density and magnetizing force equals to zero. So that means the CT is now demagnetized. Alternatively, if you have a source for variable voltage with constant frequency, you can also do that. You can use that. And if you have constant voltage with variable frequency, you can also do that. And if you have a DC current, which is alternating DC current, meaning positive side, negative side, like this, then you can also use that to demagnetize the CT. So, but the ideal is, of course, the ideal is to bring back to zero in this diagram, as you can see here. So by using these three methods here as alternatives, the most important thing is to bring it back to zero here. Now, before stepping on to the ratio test, I would like to discuss first the CT equivalent circuit, or the ideal CT equivalent circuit. So for ideal CT, what we mean here is that there is no losses. There is no losses which corresponds to excitation current. So as you can see here in the diagram, excitation current cannot flow anywhere because it has no connection here in this diagram. So in this circuit here, this determines, or this displays an ideal CT equivalent circuit. So in ideal CT, the ratio of the current primary over the secondary current is exactly equal to the number of turns on the secondary divided by the number of turns on the primary. Exactly equal. Again, this is ideal CT. And when you look at the phase angle here, so what comes in exactly at 0 degrees will comes out at 0 degrees on the secondary. This is ideal CT. And that is zero excitation current. But of course, in the real world, it's not ideal. Sorry. But in the real equivalent circuit, we have losses. We have errors. And that is caused by excitation current. So in that case, by using the Kirchhoff's law, we have the primary current divided by the turns, and that is equal to IS plus the excitation current. So the ratio will be rated primary current divided by, the secondary current plus the error, which constitute to excitation current, is equivalent to the number of turns secondary divided by the number of turns on the primary. So as you can see here in this formula here, the excitation current is being affected by this burden or your load. So this load could be relay, this load could be meter, and this load could be other devices for SCADA, for example, like transducer. So again, the losses, excitation current is being affected, please remember that, is being affected by the load here, right? Now, what happens if we have excitation current? So again, as I mentioned, if it is ideal, then the primary current is in phase with the secondary current. However, if there is excitation current, there will be a little bit discrepancy here because of this displacement or this phase angle displacement caused by that excitation current. And again, this excitation current is being affected, or this load is affecting the excitation current. Now, going to the ratio, we have two methods in testing the ratio of the CT. Number one method is the primary injection, wherein we inject current into the conductor or the primary conductor and measure the secondary current flowing into the secondary side. Another method is the voltage method, but this time, because it is voltage, then we inject on the secondary and measure the voltage on the primary. Now, looking first at the current method. So a suitable current below saturation is applied to the primary winding, and the secondary current is measured, as you can see in the diagram. Then the turns ratio is approximately equal to the ratio of primary current divided by the secondary current. Looking at the voltage method. Actually, this voltage method is from the principle of ideal transformer, that what comes in will goes out in terms of power. Power in is equals to power out, and the power formula is voltage times the current, and also in the power out, we have the voltage secondary times the secondary current. So I am assuming here that there is no losses, all right? So please take note of that. So in getting the ratio, for current, we have I1 over I2, but for the voltage is the reciprocal. So we have the voltage secondary divided by the voltage primary. Same thing, This is the current method. This is the voltage method. However, when we do the voltage method, we inject on the secondary side. This is good to do, or this is applicable for cities that are connected in bushing, for example, wherein we are having difficulty in injecting primary current. Imagine this is a transformer and this is a bushing city. If we inject higher current into the transformer winding, then I don't know what will happen. It might burn up the winding, you know, if we inject a higher current. Same is true if you have a breaker here, and if you have a bushing city, and the primary is difficult to access, then you do a voltage method. So in the voltage method, a suitable voltage below saturation is applied to the secondary. The turns ratio is approximately equal to the ratio of the secondary voltage. And for metering application, plus or minus 1% for the ratio, and plus or minus 9 radian or 3 minutes for phase angle. For other application, it could be plus or minus 1.2% for ratio, and plus or minus 1 degree for phase angle. So again, it is normally, or no, not normally, but it is a solution to test a bushing CT, the voltage method. However, we have challenges in connecting into the bushing CTs. So in the manual of one of our tester, the MRCT, you can find this suggestion, or not a suggestion, but the actual diagram on how to test the bushing CTs. So for example, if you have a Y winding transformer and the delta on the low voltage side, what you can do in order to test the ratio here, you must short the secondary. This is to cancel out the inductance on the secondary, and then we inject on the secondary the voltage on the terminal box or the control cabinet, and then we measured the voltage on the primary terminals of the transformer. Because again, this is a bushing CT, so the CT is normally built into the bushing of the transformer. Now, this one is an example of the delta winding transformer. So here again, we shorted the secondary winding before we do the injection in the control cabinet and measure the voltage on the primary terminals. Okay. Now, another test for the CT is the saturation test. When we do the saturation test, we apply the voltage on the secondary side, as you can see here, of the CT, and the current flowing into the winding of its selected value of voltage is recorded. Right? So we have a voltmeter here, we have a voltmeter here, and also we measured the current here. And we read the knee of the excitation curve are especially important in plotting comparison curve, as you can see here in this example here. But before going to the procedure, I want you to understand the basic of this saturation of the CT. Why it became saturated? Why the CT is having this saturation? So when you have a primary current flowing into the primary winding, there will be a magnetic field produced by that flowing of current, by that flow of current. So there will be a magnetic field. And this magnetic field will cause a magnetic flux to flow into the core and goes into this side of secondary, as you can see in the picture. Now, when the secondary has a load or connected to a load, there will be voltage across to this load. And what will happen if there is a voltage across to the load or the secondary winding? There will be a secondary current. But again, you have a flowing current here, and that will cause his own magnetic field. And again, if you have magnetic field here, there will be an opposing magnetic flux opposing this coming flux from the primary side. Okay? But there will come a time that only because of too much current on the primary, there will come a time that only the magnetic flux is stronger on the primary side, coming from the primary side, and it will not be opposed by the secondary side. So we all know that a CT core is composed or of a fixed number of dipoles. And at some point, when the current is flowing and it's getting high, at some point, these dipoles get aligned and it becomes stronger than the opposing flux. And there will come a time that this opposing flux cannot cancel anymore the one from the primary, and at that point, that the opposing side cannot cancel anymore, that point is the saturation point. Meaning, when I reach the saturation point, there will be no voltage here across the secondary. And if there is no voltage here at the secondary, then there will be no current flowing on the secondary. That is more than the saturation, actually. Okay. That means that our CT is saturated. No more current, or the current, if it has a small current, then it will not be accurate anymore. So the saturation point means that is where my CT can provide or can produce a signal that's still accurate for my application. So these are the examples of the excitation curve. And in here, as I've said, we have the saturation line here. This is the saturation point. And for the ANSI standard, they use tangent 45 degrees and tangent 30 degrees. Tangent 45 degrees is used for the non-gap course, and the tangent 30 degrees is used for the gap course. So as you can see is the line, then we will draw a tangent 45 degrees, and where the line that touches this curve, and that is the point of our saturation. So again, they have different definition, these two standards. So for the ANSI, that is the point on excitation curve where angle 45 degrees or 35 degrees line is tangent. For the IEC, it's different. So we are looking at the change in excitation voltage in the change in the excitation current. So if it happens that my excitation voltage having a change of 10%, and in result, I have a 50% change in excitation current, then according to IEC, that is my knee point. Okay? So these are just an example here. Another test for the CT is the polarity test. So this is different from the DC polarity, which is we have the positive and negative. When we talk of instrument transformer or CT, polarity means the direction of the current. So normally in the CT, you can see a polarity mark. So that means that is where the direction of the current is starting from. Okay, so we also need to check that. So we have a correct reading or a correct signal going to our protective relay or to our meter. So polarity test, this proves that the predicted direction of the secondary current flow is correct for a given direction of primary current flow. So polarity marks, this is designated by this dot here, designates the direction of the current. So here, as the primary current is entering the primary terminal, the corresponding secondary current is simultaneously leaving similarly marked secondary terminal. So that is how the polarity test. And according to ANSI C57.13, that one series 2006, we can test the polarity through phase angle method. So in this method, we inject an AC test voltage of magnitude less than the CT knee point voltage, and the phase angle between the primary and secondary voltage are monitored. So if the result is 0, then we got a correct polarity. But if we have 180, that means on the other side or the other direction, and that will be a wrong or incorrect polarity. That is according to ANSI standard. Now, the burden test. Burden of an instrument transformer, that property of the circuit connected to the secondary winding that determines the active and the reactive power of the secondary terminal. The burden is expressed either as total ohms impedance with the effective resistance and reactance component, or as the total volt ampere and power factor of the specified value of current and voltage frequency. Now, when we do the burden test, we are not testing, in our case with the MRCT, we are not actually testing the CT here. We are testing the load of the CT. So we are getting how much VA or how much ohms is having with this burden, what we are having with this burden here. So what we do, we compare the result, our result, the burden that we got with the nameplate of the CT. So that means if the burden that we've got is more than the nameplate of the CT, then that means our CT can no longer be accurate because we have high burden or we have high load. Okay. Now, burden test, it verifies that the CT will maintain its specified accuracy under a specified set of load conditions. So it ensures that the CT is able to operate connected devices within its operating characteristic. It is expressed as either VA and power factor of specified value of current, total impedance with respect to both resistive and reactive component. These are just an example of the burden table. So if you have a secondary terminal voltage of 10, then you can have a maximum burden of 0.5 ohm, 0.1 ohm, sorry. And for example, you have a class 100 as class 800 CT, then that could give you up to 8 ohms of maximum burden. These are the tables. Anyway, I guess we will give you this presentation, so you can refer this table, and you can find this table also in the standard. And this is also from the standard. These are the limits. So for metering class of 0.3, and if you are looking at 100% rated current, the accuracy must be within this range, 0.997 to 1, 1 as the maximum, 1.003. And if you are going to inject 10% of the rated current, then the minimum value of accuracy that you should get is from 0.994 to the maximum of 1.006. And this one is for the voltage transformer. So if your voltage transformer is 0.3, the minimum should be 997% up to 1.003 at 90% to 100% rated voltage. So now again, with this curve from manufacturer, this is just an example of the excitation curve or the saturation curve. It in the result after you test, you can clearly see if the CT behaves something like this on what you got from the manufacturer. So in here, you will see that when I have this excitation voltage, again, this excitation voltage is caused by the primary current from the as you have seen in my diagram before, that as you increase the primary current, then you increase the voltage across the secondary winding. So when you increase the voltage across the secondary winding, then you will have excitation current. And what does it mean, the excitation current? As I've said a while ago, these are errors. So as you go high voltage, and when you are above this line, then your CT is no longer accurate because you are giving or you are having higher excitation current, as you can see in this table here. And these are just some example of the error limits for class C and T classification. At rated current should be at 3%, and at 20 times it should be 10%. So this is just an example. In the metering class CTs, normally our tester provides this parallelogram. So how can you, what is the use of this parallelogram? This parallelogram, you can use this in doing the ratio test. So if your ratio test falls outside the box, for example, you injected 100% rated current, and then your ratio is on outside because the value of the phase angle is, for example, plus 10, right? And we already considered the correction factor, and that means our ratio test is failed because it is outside of the box or the parallelogram here. And for example, I inject 10% of the rated current and my ratio falls outside, then that means my CT fails. Okay. So yeah, these are from the standard. So you can see this in the standard. As you can see, if you have a class 0.3, the accuracy guaranteed from 10% rated current up to 100% of the rated current is 0.6. And the accuracy guaranteed from 100% of the rated current to 150% of the rated current is 0.4. This is just how you interpret this one. And this one is available on this standard here. And also this one, this curve, which means as you go high on the percent of the rated current, for example, you get a 100% rated current, then you have a phase angle in minutes lower. So as you go high on the primary rated current, you get a lower phase angle deviation. That is how what means. And so the same as true in this ratio correction factor here. So for different standards, we have the IEEE C57.13. This is a standard requirement for instrument transformer. We have a standard for field testing of relaying current transformer. We have the IEC standard for instrument transformer, that is the IEC 60044-1. And these are the ANSI standards, and these are the IEC standards. With our MRCT, we can do a simultaneous 5 taps, as you can see here in this diagram, when we do the test. And yeah, it almost do everything already. Now, let's talk about the voltage transformers. So again, voltage transformer, like I've said, is just a similar to the power transformer where you have the primary winding and the secondary winding. So talking about the magnetic voltage transformer, and this is the equivalent of circuit of the voltage transformer. So normally, when you do the turns ratio test, the number of turns is directly proportional to the voltage. And the voltage equivalent circuit referred to the secondary side. As you can see in this diagram here, we have the resistance on the primary, but in this secondary side, we have the resistance on the terminal, and we have the resistance on the winding here. And we also have this excitation current. And typically, the saturation curve for the voltage transformer is looking like this, looks like this. And normally, the saturation is at this 100% primary voltage. So this table here represents or shows the standard burdens for the VT. So we have these markings in the VT, W, X, M, Y, Z, and ZC. And these are the corresponding equivalent or the volt ampere. And this is the corresponding power factor per different burden, as you can see here in the table. And for the voltage transformer accuracy, we have 1.2, 0.6, and 0.3, for example. And we have these limits of ratio correction factor 1 to 0.99. And the limits of the power factor lagging is 0.6 to 1. So these are just an example of the accuracy classes of the VT. And when you try to do the frequency response or to get the frequency response of the VT, this could be this what you can see in the frequency response of the VT. Now, the typical field test for VTs. Again, like the CTs, we can do insulation resistance, we can do winding resistance, we can do saturation and excitation, we can do ratio and phase deviation, we can do short circuit impedance. So for the insulation resistance, it's the same as the CT. We do the primary to secondary winding insulation, we do the primary to ground insulation, and we do the secondary to ground insulation. This is according to ANSI C57.13, that's 2006. So with our MRCT here, as you can see, because it is a voltage transformer, we must take extra careful. We don't want to do a step up voltage here. Okay, so normally when we do the ratio test for voltage transformer, like the power transformer, we inject or we do the step down. So we inject on the primary side and we measure on the secondary side. Okay, this is what we are doing in the voltage transformer. And for the VT saturation, like the CT, we do the injection on the secondary side and we leave the primary side open and we get the voltage knee point and the current. So take note, it is we are injecting hazard high voltage. Remember, we are injecting on this on the secondary, but since we are injecting on the secondary and we are doing the saturation test, our tester injects slowly, ramping up, so it will not reach, you know, the dangerous voltage across the primary side. Okay. And when we do the winding resistance test, again, we only do it on the secondary side. Of course, when we do the winding resistance, the limitation of here is that the capability of the test equipment to inject on the windings. So here in our MRCT, we inject on the secondary side, not on the primary side, because the primary side has more turns. That means that it is a higher resistance there. Okay. And yeah, so we do, and we get the resistance reading. And if we have any other VTs at the same specification, so what we can do is to compare the resistance reading that we got with the other resistance reading of the other VT. So we can also do with our MRCT, or the test that we can do with the VT is the short circuit impedance. For the short circuit impedance test, an AC current at nominal frequency is injected on the secondary side, and we get the response of the reactive element. So again, please watch out. We have this hazardous high voltage because we are injecting on the secondary, and so technically we are doing a step up test. But with the short circuit impedance, we short the primary winding like this, and we ground it, so it's still safe, and we are just getting the response of the reactive elements. And by the way, just a point to note, we must ensure that we have a good shorting when we do the short circuit impedance test. So otherwise you can see some spark if it's not good, or you get a higher reading, or the test cannot be performed because the shorting is not good. So please bear in mind that when you do the short circuit impedance, the shorting on the primary side must be really, really good. Now, looking at the capacitive voltage transformers, the capacitive voltage transformer is an acronym which stands for capacitive voltage transformer, and is type of VT or BT, potential voltage transformer, and commonly used around the world. CVTs are only available practically above 69 kV, where their cost and size becomes an effective solution for providing secondary voltage. So mostly this is for the high voltage application, the CVT. So a CVT or any PTBT has one primary purpose: to transform high voltage between 69 to 800 kV down to a voltage signal between 69 to 120 volts, which is easy to handle for intelligent devices such as protective relays, SCADA system, or metering of power when used together with CTs. Typically, the components of the CVT, as you can see in this diagram, so I will not go into details of these components of the CVT, but as you can see in the diagram, we have a lot of components, and it is noticeable that we have capacitor divider here, and we have transformer. And looking at the CVT structure, again, we have the capacitor, we have the compensating reactor, and we have a step-down transformer before it goes to the relay, right? So in this diagram, you can see the ferro resonance suppression circuits. This is the active. As you can see here, using the step-down transformer on the secondary, goes to the relay. And this one here is the passive ferro resonance suppression circuit. Now, the typical field test for CVTs, I am not, I don't know the other, but what I can see or what I can share with the testing of the CVTs, we can do insulation power factor test or tan delta test. We can do the ratio and phase deviation test. And actually, if I may add, sorry, I forgot to type it in. We can also do, because we have the C1 and C2, then we can also do the capacitance test. And we will be discussing that on the later part. Now, CVT testing. Accuracy, the importance typically associated with CVTs is ratio accuracy. As we know that incorrect voltage will lead to large error in metering of power and improper tripping of transmission lines and substations. Now, when we do the CVT ratio test, this is optional to many utilities nowadays. And some utilities apply a high voltage on primary and record secondary voltage using a multimeter. This is the traditional practice. This gives us an approximately ratio calculation which proves that the CVT work as a whole. So this method has some drawbacks, of course. We cannot achieve a significant level of accuracy because of both the high voltage voltmeter accuracy of the insulation test set, which is typically plus or minus 1%, plus the multimeter accuracy of plus or minus 0.5%. So the resulting total error could be plus or minus 1.5%. So it's not accurate. So the error exceeds the total error limit of the most CVTs. So this method is also considered dangerous, as which prevent usage element of danger if operator handle multimeter while voltage applied. We have a tester, the MRCT, that can test a CVT ratio. So here, with our MRCT, we inject up to 2000 volts, injecting at the primary side and measure at the secondary, on the secondary side. So since this is a CVT, then a high voltage is needed and a good test leads for 2 kV injection must be considered. Not just the ordinary test lead, but this is a special test lead used for 2 kV injection. So it could be accurate when you do the CVT testing. That is how our MRCT do the CVT testing ratio. We have another test equipment for testing the CVT. So when testing a CVT, one typical requires a 12 kV tan delta test unit for the capacitor stacks, since we have these capacitors when we have the CVTs, which can number up to 4 times the 765 kV. So each stack is measured with values recorded. Also, test which is performed by the IPF or tan delta unit, the Delta 4000 or the trucks, is the ratio and phase test. And I will show that to you on the other slide, on the next slides. So this is performed with the Delta 4000, the ratio, together with the optional 10 nanofarad capacitor, right? So when we do the capacitance and dissipation factor test of the CVT, we do these connections. So these are the typical connection, as you can see in the diagram. We measure the C1, we measure the C1 to C2, and this connection here, and we normally use in here the GST to ground, and here is the UST measure red. So the figure 1 is for a single stack CVT. As you can see, this is the figure 1. Oh, it's not in here. And the figure 4 here is for the 2 stack CVT. So readings are compared to nameplate for each stack after a temperature correction. which is provided by the manufacturer normally. And then nameplate as found readings are recorded. Then testing is complete. Test voltage applied is typically 10 kV, but this does not stress the stack insulation. Remember that. So a 10 kV test voltage is used because of historical testing method, which is defined by the other, the other brand as well, and can help in eliminating the effect of noise suppression. That's why we need to inject 10 kV because we are doing trending here of the result. We are comparing the previous test result to the test that we've got, for example, at this moment. Okay, and we use the 10 kV test voltage because we want to eliminate the noise. Okay, we need to suppress the noise. With our test equipment, this is how you connect the CVT with the Delta 4000. So warning, we inject a 10 kV. So a serious safety consideration must be uh, think, think, think of. With the CVT ratio test, using the tan delta unit, again, we need a reference capacitor which is normally rated 10 nanofarad. So first, what we do is to test the reading of the capacitor if it is really 10 nanofarad, but we only inject 500 volts in here. No need to inject a higher voltage. We are just getting the reference capacitance. All right. Now, after getting the reference capacitor, what we do is we connect it in series on the secondary voltage here when we do the ratio of the CVT. Okay, so once the reference TTR value capacitor values are known, we apply test voltage to the CVT. At this stage, it is important to note that we applied 12 kV because CVTs are not linear device with ratio or phase, and it can be affected by test voltage. So another important point related to test voltage on the primary is the resulting secondary voltage. At 12 kV on a 765 kV CVT, the secondary voltage will be 1.875 voltage AC full scale. So to measure 0.1% of this result, we are required to accurately measure the 0.18 millivolt for achieve our ratio the phase measurement. So we need a high voltage or 12 kV to inject in doing the CVT ratio. Now, to summarize this webinar, so instrument transformers, CT, whether VT or CVT, these transformers play an important role in power system. So for metering and protection applications especially. So to ensure optimal performance of your instrument transformer, we recommend a checklist of tests to be performed and the best way to perform them. So for the CT, these are the tests that we can do: insulation resistance, winding resistance, saturation and excitation, ratio and phase deviation, polarity, burden, and CT demagnetization. For VT, we have the insulation resistance, winding resistance, saturation and excitation, the ratio and phase deviation, and the additional short circuit impedance. By the way, the short circuit impedance, if I forgot to mention, this will also determine if we have some deformation inside the VT. Okay. And for the CBT, we have the insulation power factor or tan delta testing. We have the capacitance testing. This is the testing of the stocks of the CBT. And we have the ratio and phase angle deviation test for the CBTs. So as you can see in the picture here, we have different test equipment that can do testing. So here we have the MRCT. This one can do a lot of tests for the CBT in one play button. And the advantage of this one is we can test simultaneously 5 taps. So if your CT has 5 taps, then you can test it in one injection only. Just press the play button and it will give you all the results, including the insulation resistance, winding resistance, ratio, etc. And if you want to do a CBT testing, then I can recommend these two, the Trax and the Delta 4000, wherein you can achieve the 12 kV injection And also, but of course, you need to remember that you need the reference capacitor, the 10 nanofarad capacitor. So that is my presentation for today, and I guess let's move on to the question and answer portion. All right. So we have question here. Are you in, Sumedi?
Yes, Michael. I'm in.
Okay.
Yeah, we have
Yeah.
many questions actually. I will read some
Okay, you can
questions.
read, bro. Okay, okay, sure.
Okay. I think I will start from the first question from Mr. Pandu. I think this is I can answer. What the
Sure.
consideration to define the burden number of CT? So I think actually to consider the value of burden CT, you need to know first the burden of the load. Means you need to measure the load of mostly the CT will be connected to the metering or uh, protection. So from both equipment, you need to know how much the resistance or of load VA on any equipment that will be connected to your CT. So in example, if you have the VA maybe 2 VA, mean you can calculate the current voltage mean by ohm law. VA means voltage multiple current. If you know VA, you know the current, and then you will define the voltage, the drop voltage. From drop voltage, you can calculate the resistance of the total load. So mostly in any equipment like relay and protection, you can see on the data sheet the resistance value. So you can total sum all resistance in your system that will be connected to the CT and make sure the resistance value or VA value less than the VA nameplate on your CT. Yeah, I think it is my answer.
Yeah, that's correct, bro.
Yeah.
So
The
another
sec
question here. What? Okay,
yeah.
sure.
The second question is from Manoj Manhas. Why burden is not specified for PS cores of CTs? What limits loading of PS core? I think you can maybe
Well,
to answer, Michael.
uh, I'm not sure of what is PS4, but
PS type,
maybe we
PS
can.
type, TPS type CT.
Why
Mostly,
burden is not? Why burden is not specified for PS4s of cities? Well, let me get back this through email. I guess I'm not sure of this one. Right. So the
okay.
other question he has is in VTs connecting loads burden actually reduce the ohmic burden. So what is limit for loading VTs? Can you answer
What
that,
is
bro? Connecting
so what
loads
is
burden
limit
actually reduce.
for loading VTs? So I think this question related to the previous question. Yeah, the problem on the TPS CT, we don't know in the nameplate the burden information. I think we just know maybe only the
Yeah, we don't
percent.
know why it's not. We don't know why it is not specified. Actually.
Yeah,
So we will ask somebody who can answer this. I
yeah.
don't know why it's not. It was not specified.
Okay.
In BTs connecting load burden actually reduce ohmic burden. So what is limit for loading BTs? So yeah, that burden that was indicated in the nameplate. But if you are referring to the PS score again, then I don't know why they don't have indication of the burden. So yeah, I guess what we need to ask here is the manufacturer of that PS4 uh, uh, CTs or BTs. Okay. So another question here for 22 kV 110 metering VT test for SPPG. What is SPPG, bro?
This is
By injecting.
the utility company electrical in Singapore.
Okay, okay. Sorry, I don't
Yeah.
know. So for 22 kV and 100 volts metering VT test, by injecting 200 volts across primary, Is there an IEC or IEEE standard of results to refer at the secondary side? So what test are you referring here, sir? Ratio?
Yeah, I believe this is ratio test.
Or
I believe.
if that is the ratio test, then you need to check the class of the VT, and it has a corresponding limits according to the standard, as I've shown in my presentation. Another test for ratio test. Why do you use secondary injection test for PT and primary injection test for CBT? Can we use both secondary and primary injection? Yeah, this is for safety reasons, sir. So when we do VT testing, we normally inject not on the secondary, but we normally inject on the primary. This is to avoid stepping up the voltage, because if you are going to inject on the secondary side, if it is VT, then there could be a voltage transformation on the primary side, and that could result in stepping up the voltage, and you might produce a high voltage on the primary side. So imagine if you have a 13,000 volts is to 115 volts on the secondary, and then you inject 115 volts on the secondary, that can produce 13,000 volts on the primary. So that is very unsafe. That's why when we do the VT testing or the PT testing, we do a step down and we inject on the primary side, not on the secondary side. Also the same as the CVT. CVTs are used for the extra high voltage. As you have seen in my slide, it started from the 69 kV system up to 800 kV system. So it is a really high voltage equipment or instrument transformer. So what we can do is to inject on the primary to be safe, and yeah, so to be safe. What is the purpose of compensating reactor and ferroresonance circuit in CVT? Is it always provided for CVT, not only for resonance? Yes, sir. The compensating reactor is to compensate the capacitance that is produced by the stacks of the CVTs. So we need some compensating to lower down, to have a resonance. So in order for us to measure. Hi, Michael. Question is there any benefit if we do sweep frequency testing ITC on CBT? Yeah, the benefit of this one is to check the response of the instrument transformers. And again, if we do the sweep frequency response, then it is a fingerprint testing, meaning we compare the fingerprint and we do if we have some deformation in the transformer. But yeah, when we do the VT testing and we do the sweep frequency response testing, then we do inject low voltage signal and we varied the frequency. So it's a safer way. And yeah, when we do, as in my presentation with the previous about the sweep frequency response, when we do the open circuit, then we can already have the excitation current, for example. When we do the interwinding inductive, then we have the ratio already, something like that. Okay, so we can do that. We can also do that in a safer way.
I think the last question: what is the accuracy of the PX class CT? The PX class CT, I think around 0.5%, as I remember. PX class is, if I'm not wrong,
0.5%.
yeah, 0.5%.
Yep, that is the accuracy error percentage. So I guess
Okay.
that's all what we have for today. And again, thank you so much everyone for attending this webinar. Hope to see you again next time with the other webinars. We have a lot of webinars coming in, and we will be sending this recording of presentation in 2 days time. together with the certificates for the attendees. And again, thank you so much for attending, everyone, and stay safe. Thank you, Zoom, and thank you, Grace.
Thank you, Michael. Thank you, everyone. Thank you, Grace.
Thank you, everyone. Bye bye.